Swayam Prabha. Digital India. Educated India.
So you use some kind of a heuristic. Let me just quickly go to one of the heuristics and then talk about it. So this is the cycle-based scheduling, and what you try to do here is that you have your dependence graph, you calculate all the earliest start time and the latest start time, and maybe you use the slack as the priority or whatever. Then what you do is that in each cycle you will start scheduling the nodes starting from the source node or the node which does not have any input arcs to it, because that node is ready at time step 0. And you start scheduling this such that at every time step, right, you see which of the nodes are ready to be scheduled, and among the nodes which are ready to be scheduled, you choose the one which has the highest priority, and then you see whether that node can be scheduled in the current time step. That means that you have enough resources for it. And once that node is scheduled, you can mark the dependent nodes that their dependent values would become available in that's execution time plus D, which is the execution time for that operation. I'll just quickly talk about that over here. So you start off with an empty, you start off with your dependence graph and your initial schedule is empty. Then you put all the nodes which are the source nodes into your ready queue, and you prioritize them, prioritize based on the slacks that they have. Then you start taking nodes from the ready queue and schedule them, right? If there are no resource conflict, you will schedule them at the same cycle, right? And you will introduce them in your schedule. And you remove that nodes from the ready queue, right? And then you keep scheduling all the nodes in the ready queue as much as you can for the current cycle. Once you have exhausted all of them, or once you have used all your resources, you will go to the next cycle. And in the next cycle, you again see which nodes have become ready. For example, let's say if the source node has produced a value after time step 1, then the nodes which are dependent on that would have become ready, right? So you mark those things subsequently, and then they go into the ready list. Again, you prioritize the ready list. You keep doing the schedules again and again. So this is how cycle-based scheduling works. There is something similar which is called operation-based schedule, where you don't go cycle by cycle, but you pick an operation and you try to schedule it between its earliest start time and latest start time. Of course, you have to do certain adjustments if some nodes cannot be scheduled between the earliest start and latest start, and so on and so forth. So there are some levels of details here. I will not go into that, but that's really what you do. Okay, but let me just quickly explain this with the help of an example. So if this is my dependence graph and I want to schedule it in for a machine which has, let's just simply say that I have 3 functional units, right, or 2 functional units in which I wanted to schedule. Then the numbers that I have shown here is the earliest start time and latest start time. And I try to schedule these nodes in these various time steps. And you can see that by doing this, I am making sure that all the dependencies are satisfied. For example, if subtract is scheduled in time step 1, then multiply, which is dependent on subtract, is scheduled at least 1 cycle later, right? This add, which is dependent on the multiply, is scheduled 3 cycles later, and so on, right? So the dependence graph captures the dependencies as well as the amount of time that each of these nodes take. And in this, what is called the reservation table, I kind of make sure which resources are being used in what cycles, right? Okay, ignore the pop window, right? So this is one schedule that is possible, where I have tried to schedule add 1, and in the next cycle I have scheduled add 2, because I have only one integer function unit in which I have to schedule both add 1 and add 3. Both of them are ready in time step 0, but let's say I scheduled add 1 and then after that I scheduled add 3. But in time step 1, I would have actually both subtract 2 as well as add 3 to be ready. But in this case, I have scheduled add 3 in time step 1 and subtract 2 in time step 2. Because subtract was scheduled in this time step, multiply is scheduled 1 time step later, and of course the dependent add is scheduled in cycle 6. But instead, if I have scheduled subtract 2 instead of add 3 first, right, I would actually get a better schedule, right? For example, if I have scheduled add 1 and then subtract 2, then multiply can be scheduled 1 cycle earlier, and therefore the add also can be scheduled 1 cycle earlier. This add, which is not in the critical path, is scheduled 1 cycle later in cycle 2, and the dependent load instruction is scheduled in the next cycle, but anyway, the load completes before something, the add completes or whatever. So this is a better schedule than this one, and that is because in this schedule, right, you have to realize that these nodes are in the critical path, right, the nodes that I am marking, right, those nodes are in the critical path, and these nodes are not, right, and by scheduling a node which is from a non-critical path early, right, this schedule has got additional number of cycles, whereas in this case, the node which is in the critical path is given priority, and therefore you got a better schedule. That's the idea, right? Okay, now let's just move on to the global instruction scheduling. So you could do basic block instruction scheduling, which is nice, but the problem with basic block scheduling is that basic blocks are too small. You typically have only 6 to 10 instructions in most of the basic block. The average number of instructions is somewhere around 5 or 6, right? And therefore, you have very little opportunities for doing instruction scheduling, particularly when you have functional units which take a large number of cycles, for example, multiply, divide, and so on. So you have very little opportunity. And this is where optimizations like or transformations like loop unrolling helps, because when you unroll the loop, you essentially bring in more iterations of the more operations into a single iteration, and that essentially helps you to increase the basic block size, right? But there are limitations even for doing loop unrolling, because when you do loop unrolling, you increase the code block size, and that causes certain other problems also. So you may want to talk about doing instruction scheduling beyond basic blocks, right? And particularly you want to talk about instruction scheduling for loops and other things. So let's see how we are going to do this. So I will just take a very quick example here. There is again a simple program here with a for loop and a conditional statement. These are the sequence of instructions. Let's not worry about what they are. And these are the basic blocks, and this is the control flow graph, right? Now, if I try to do basic block instruction scheduling, then essentially it means that I can do whatever instruction scheduling I want within a basic block. But each basic block acts like a boundary, and instructions cannot move across basic blocks, right? So let's say that I try to schedule this for an architecture with 2 functional units, and let's assume that load and dependent instructions take 1 cycle in between, right? Then this is what that happens. Because this branch instruction is dependent on the load value, there has to be 1 stall cycle, and similarly this this load instruction and the dependent add instruction, right, need to have 1 stall cycle in between. I have to leave the stall cycle and so on, and this is the maximum that I can do, because this add instruction produces a value in R4 which is being used by the store instruction. So you can see that there is a sequence of dependencies in basic block B2, and this is the best that I can do as far as B2 is concerned. So if I do basic block instruction scheduling, I end up with too many stall cycles because I don't have enough instructions to reorder them, correct? And the boundaries are kind of restricting me in terms of doing certain things. So the idea of global instruction scheduling is, what if I allow you to move some instructions from basic block B2 or B3 to move and then scheduled along with B1 or scheduled along with B4? What happens? And again, when you do such a thing, you also have to make sure, right, that all your dependencies, data dependencies and control dependencies are not violated. Because if they are violated, you're going to end up with a program which is not going to produce the same result. So let's see what happens. I'm going to kind of do this very quickly because we don't have a lot of time. So there are many ways of doing this, and I'm going to talk about 2 of them. One called the trace-driven a trace-based global scheduling. The other one is called super block scheduling. There are also other kinds of methods which I have listed here, right? And let's just see what is the objective. The objective of a global instruction scheduling is that don't worry about these individual basic blocks or don't worry about certain paths. As long as you can reduce the overall execution time of programs, right? Even if you try to increase the complexity, even if you try to increase the number of instructions which are executed in the other paths, right? It's okay to do that as long as you are able to reduce the overall execution time. So let me just quickly go to the example and then show you what that means, right? So here is the basic block. Here is the sequence of instructions, and this is the control flow graph. Supposing, let's say that the then block is taken more often than the else block, right? It's often possible that in your code that certain path is taken more often than others, and you can identify this by means of profiling or by means of having a knowledge about the program and so on, right? And when you know that, right, it makes sense to optimize the path B1, B2, B4 than the path B1, B3, B4. In fact, it makes sense to optimize the path B1, B2, B4 even at the expense of a path like B1, B3, B4. Correct. So that's exactly what we are going to do in trace scheduling. Identify the trace or the sequence of basic blocks which are going to be executed more often and try to do more aggressive instruction scheduling on the path, right? Maybe introducing some additional code on the other paths, because when you try to move instructions from, let's say, basic block B2 to B1, you may be moving certain instructions, right, whose effect should not be seen on basic block B3. Therefore, you have to possibly introduce some compensatory instructions on this. That is fine as long as you don't, as long as you optimize on this path, even at a small expense of this path, go ahead and do it so that your overall execution time is minimized. This is the idea. So let me just quickly show you in terms of the instructions what this is, right? So again, I have taken the basic block. The idea is to see whether I can move these two instructions to the basic block over here, right? And when I do that, I can actually execute two load instructions together, and then the add and branch instructions can be put in some way. That's the whole idea. But in order for me to do that, remember that I'm going to modify the value of R3, and therefore if the sequence of instructions I have in the else block, if R3 is live in that, then by moving this instructions, I would do some harm to the program. So I will not be allowed to move this load instruction if R3 is live here. Or if R3 is live here, I have to introduce certain compensatory code, right? Maybe copy R3 into some other register or whatever, right? Before I could, right, go to this path. So I have to see all of those things when I do the instruction movement. But in this case, since R3 is not live here, similarly R4 is not live here, right? I can actually move these two instructions here. Fortunately for me, R4 is defined before it's used. Therefore, it is okay to move R4 again, right? So when I do that, I can actually get the following sequence of code. I have two load instructions executed in parallel. Then the branch instruction and the add instructions are executed in parallel. Then the store instruction, which is the other instruction in the then part, is executed. The branch instruction is removed because I'm going to put the sequence of code just below that, so it's actually going to fall through, right? And then on the else branch, what I do is that I execute instructions I7 and I8, and then I branch back into I9. So if you look at it, the then branch is going to take 6 cycles. There are some details here, but the then branch is going to take 6 cycles, whereas the else branch will take 7 cycles because you go through this particular control flow path, right? So what we have done is that we have essentially gone from that several cycles for executing the basic block scheduling to something which is much more improved. So here what we have done is that we have introduced the notion of traces, which are more than basic blocks. Basic blocks, the way they are defined is that they are single entry, single exit. That means that once you enter into the basic block, you will execute all the instructions. Whereas when you talk about a trace, right, the trace will have multiple entrances and multiple exits, right? And that is the point about trace. We will talk about something called a super block, which is something which is in between, which will have a single entry but multiple exits, right? So the same program, again, I'm going to, because of lack of time, I'm going to skip some details and then go and talk about super block scheduling, where we are going to actually talk about this in the following way. The same control flow graph, I want to have single entry, multiple exits, possibly multiple exits. So I rewrite the control flow graph in the following way, that is, duplicate the node or clone the basic block B4 into two parts and then write it like this. And now I have one super block which is consisting of B1, B2, B4, right? And the entry is always from B1, correct? And it has two exits, one at the end of B1 and one at the end of B4. I have another super block which is consisting of B3 and B4, entry in B1, exit only in B4, right? Now I can individually schedule these nodes or individually do instruction scheduling for these nodes so that I can optimize the instruction schedule length. That's the idea. Okay. Again, if you go through the slides, you will figure out how we have done that. And in this particular case, the super block, which is consisting of B1, B2, B4, will take 5 cycles to complete, and the super block, which is taking B1, B3, B4, will take 6 cycles to complete, right? Because of certain optimizations that you were able to do. Again, in the interest of time, I'm not going into all the details, but you can, I will give you the slides, you can go through them, and then if you have questions, I can come back and talk about that. Okay, now you can enhance the super block by doing loop unrolling, loop peeling, and various other transformations. Let's skip that. And there is always a relationship between phase ordering, which is, between instruction scheduling and register allocation. Let me briefly talk about this. If you do instruction scheduling first, it aggressively moves instructions, and therefore it can potentially increase the live range of variables, and therefore it can actually increase the register pressure, right? So in pre-pass scheduling, you do instruction scheduling first, which basically increases the register pressure, and therefore you may incur more spills. Whereas in a post-pass scheduling, you do register allocation first, and doing register allocation first essentially introduces anti and output dependencies, which prevent some form of instruction reordering. Therefore, you lose certain opportunities for exposing parallelism, right? So these are the two things that conflict with each other. People have also talked about integrated register allocation and instruction scheduling methods. So let me skip all of those things. Other details, some of them are there in the slides. I have hidden them here. You can go through that leisurely. Let me spend the last 10 minutes on software pipelining. All that we have talked so far is that I can do instruction reordering within a basic block. I can do instruction reordering across basic blocks moving instructions. But what happens when I have a loop? Can I move instructions from one iteration to another iteration? Or can I overlap the execution of consecutive iterations? Is it possible to do? Right? Typically in global instruction scheduling, you don't do that. Loop boundaries are essentially the barriers, and you can't move instructions beyond them. Right? Whereas in software pipelining method, you try to do that, and you try to achieve a speed up, or you try to achieve a throughput which is significantly faster. Again, I will not go into the exact software pipelining method per se, which is much more detailed, but I will give you some examples of what it is, right, by going through one program example. Again, let's look at the same code, right, where I'm trying to do A of I is equal to A of I plus S. In the case of the VLIW processor, we saw that how by unrolling the loop, we can get something, correct? I'll try to do this. I will try to achieve a similar throughput without doing a lot of unroll, right? Or at least without doing that many physical unrolls as you would see. I may do some logical unrolling. This is the same code that I have talked about, right? And this is the data dependence graph for that. I will not go into the details of this here because you're not going to do the software pipelining method in detail. So let me skip that. So again, I'm assuming an architecture similar to what we have seen before. And if you try to do the scheduling, right, this is essentially what you get, right? For the unrolled graph, this is what you get. You can see the load instruction, the add instruction, the floating point add instruction is dependent on that, and you have to have one stall cycle in between. Then there is a store instruction which is dependent on the add, and there has to be 2 cycles in between them, and so on. And the different colors of the font essentially talk about the different iterations of the loop, right? So I haven't unrolled the graph. I haven't unrolled the loop, and I have scheduled each of these things by doing simple basic block scheduling. So here I would require 6 cycles to complete each iteration, right? Now let's see that. Let's see what we can do. If I unroll the loop twice, right, then this is the code that I have. And if I try to schedule them, this is what I get. So here again, I take 7 cycles to complete 2 iterations. Therefore, potentially I'm taking 3.5 cycles per iteration, right? Okay, can we do better? Right, of course, you could have unrolled it 5 times and you could have got the schedule that you have shown earlier, but let me try to see, let's see whether we can do it in a different way. Okay, so this is basically scheduling of 1 iteration, right? And we have scheduled it in 6 cycles. Now the question is, when should we start the execution of the next iteration? If you are not overlapping, of course, the next iteration can only start from cycle 6. But let us say that your instruction scheduling method allows you to overlap, operations from different iterations. But as long as all the dependencies are satisfied, you are allowed to overlap them. So in this case, you can see that there is a dependence from load to add and then from add to store, right? But when you are doing for a of I plus 1, none of this is going to be dependent on what you did for a of I. So why not I start the next load 2 cycles later, like what I have shown here, right? Now you can see that iteration 0 and iteration 1, operations from iteration 0 and operations from iteration 1 are kind of overlapped, right? I'm no longer talking about a basic block boundary, and I'm no longer talking about keeping them separate and so on. I have now overlapped these 2 iterations. And let me start the next iteration 2 more cycles later, right? And so on. Now you can see that at some point in time, I have what is called a steady state kernel, which has actually 1 load instruction, 1 floating point add instruction, and a store instruction, plus an integer subtract, integer add, and branch instruction, which are essentially all the instructions in 1 iteration of the loop, right? But the interesting thing here is that, right, you can see that what's that? The store belongs to the ith iteration, right? The add belongs to the I plus 1th iteration, and the load belongs to the I plus 2nd iteration, right? This is iteration 2, iteration 1, iteration 0, right? So what we have done is that we have composed a loop now, which consists of the same operations as the original loop, but now the operations are being performed on different elements of the array, or different or corresponding to different iteration values, right? So this is what is called software pipelining, right? And you are able to now execute each iteration of the loop in 2 cycles. There is something called a prologue, which takes a little long. This part is what is called the prologue, which is the initialization part. This part is the kernel, which is what is going to be repeated, and this part is the epilogue. So you have 1 prologue and 1 epilogue, and you repeat the kernel n-2 times in this particular example. So if you have a very large value of n, effectively you get what is called 2 cycles every iteration. So compared to the unrolled schedule, which had a lot more number of instructions, this have fewer number of instructions, right? Because you are not unrolling it that many number of times, right? And there are some analysis which show that software pipelining is better than unrolling and scheduling and so on and so forth. But this is how your unrolled software pipelined loop for the same VLIW architecture would look like, right? You can see that load from one iteration, add from another iteration, and store from a third iteration. Actually, the blocking is wrong. I should have taken these two. Sorry, right? So there is something wrong about the way in which I have drawn that rectangle. I should have actually drawn this rectangle. This should have been my kernel, right? Sorry about that. Okay, I will correct it in the slides before I give it for uploading on the web, right? So that has actually one load instruction, one store instruction, and so on. And that is my software pipelined kernel, right? This is the same thing expressed in a slightly different form. Let's skip this. As I mentioned, you can see that load is coming from the ith iteration, then add and subtract are coming from the I-1th iteration. Then, of course, store, integer add, and branch instructions are coming from the I-2th iteration. Okay, so as I mentioned, this is the analysis very quickly. You can see pictorially what it means. If you do simply basic block scheduling, then for every iteration, there is a phase in which, every iteration is kind of limited by whatever instruction scheduling you can do. If you do unrolling and scheduling, you have something like this. Whereas if you do software pipelining, you should be able to get something like this. So this ramp up and ramp down phases are basically, once you start a new iteration, it takes some amount of time for you to get enough instruction level parallelism, or you have enough operations to keep the pipeline functional units busy. But then because you have to end the iteration, it kind of tapers down, and then this kind of starts on and off. So if you don't do any unrolling, you incur it for every loop. If you do some amount of unrolling, you incur it for once every time the number of loops is unrolled. Whereas when you do software pipelining, you incur the cost exactly once in the beginning and once in the end, corresponding to the prologue and epilogue. So this is about software pipelining. Let me take the next few minutes to just quickly say how software pipelining is done in practice. So essentially, here also you construct the dependence graph, and then the nodes correspond to the instructions that you have in your loop, and the arcs correspond to the dependencies between them. There is something called a loop carried dependence, because if you're going to produce a value which is going to be consumed in a subsequent iteration, that is called a loop carried dependence. We'll talk a little bit more about it in our lecture on tomorrow afternoon, right? Right, and essentially in constructing a software pipeline schedule, you are identifying a repetitive pattern by overlapping the executions of iterations. And if you want to know what would be the number of cycles that that determines the throughput of the software pipeline schedule, which is basically what is called the length of the kernel, or what is called the initiation interval of the software pipeline schedule, then the initiation interval is essentially again limited by two things. One is the data dependence, another is the resource constraint, right, due to processor resources. These two essentially pose two values which are called the recurrence minimum initiation interval and resource minimum initiation interval, which are the lower bounds, right, for the initiation interval. And the larger of the two would be your initiation interval. For example, dependence constraints would say that no matter what, you cannot have an initiation interval greater than 4 for this particular loop. Similarly, resource constraint can say no matter what, you cannot have an initiation interval greater than or equal to 5 for this graph based on the resources that you have and for this particular graph. Then the minimum initiation interval would be the maximum of these two things, 4, 5, which would be 5, right? So that is how your minimum initiation interval is defined. The dependence constraints, essentially because of the recurrences that you have in your program, what are called cycles, they kind of pose a minimum initiation interval. Similarly, processor resources and the number of resources you have, the number of operations that you have to perform within the loop, they pose certain constraints, and they have another lower bound called the resource minimum initiation interval. The maximum of these two would be the minimum initiation interval for a loop. you may or may not be able to construct a schedule for this for this graph with that minimum initiation interval, but you will definitely be able to construct this for a value greater than or equal to MII. So again, there are lots of approaches and how software pipelining is done, etc. I'm not going to go into those details. This is the high-level algorithm. You start off from the minimum initiation interval, and for the given minimum initiation interval, you try to schedule all the instructions in the graph using a method which is very similar to the basic block instruction scheduling method, but now you use a reservation table which is called the modulo reservation table, and you try to see whether your modulo reservation table kind of follows all the resource constraints and so on, as well as all the dependence constraints, and you try to schedule them. If you are successful, then you of course get the schedule. If you are not successful, you either try to reschedule some of the nodes in a different way, or you try to increase your initiation interval to a higher value and try to schedule them, right? So without going into all the details, just say that this is again an NP-complete problem, and there are again several heuristic approaches which have been proposed for obtaining the resource constrained software pipeline schedules, right? There are again lots of details that I have kind of skipped because of lack of time. What I will do is that I can possibly take the next 5 to 10 minutes time to take questions, and then maybe continue tomorrow, right?